I built a tower in Dublin right up to the sun. Steel, concrete, and time. I built that tower in Dublin. Now it's done. Buddy, can you spare a dime?
College Green, Dublin is the centre of Ireland's banking and commercial world. All the big banks are there. But the Central Bank of Ireland, which was established in 1942 as a controlling financial institution, had only its head office in College Green. As the central bank's finance control functions grew more and more complex, it had outgrown its own quarters and was forced to rent extra office space in several different parts of the city. Then, in 1972 came a decision to build a new central bank building within literally a stone's throw of the original location, to build in Dame Street. This film shows the progress of the building from a hole in the ground to the big bank designed by Stevenson Gibney and Associates. The main contract goes to the firm of John Sisk Co, the contractors who have already built so much of modern Ireland. Their first task is to feed the data to the Sisk computer. A manual critical path program is first prepared, using the drawings and bills of quantities for the complex. This includes more than 2,000 separate program activities, which are recorded on data input sheets, punched onto punch cards, and fed into the electronic brain. The computer digests the data briefly and then begins to print out all the programs needed by the consultants, the specialist subcontractors, and by Sisk's own project management team. These programs were updated regularly in view of the many variables in a project of this size. The job is a really big one. A 45 by 50 meter building giving 8,500 square meters of office space and a further 1,200 square meters of space in subsidiary annex buildings on the same site, which will include a fine purpose-built restaurant. Constructionally, the big bank is unusual as far as Ireland is concerned. The design provides for a large public plaza extending under the main office structure. This main structure is to be a suspended one, hanging from two tall concrete towers or cores, and it's decided to slip form these cores, and Sisk's calling the firm of British Lift Slab for the job. The huge twin concrete towers, stepped widely apart on the site, are each to contain lifts, lobbies, staircases, toilets, and ventilating and air conditioning shafts. With the plant room on the roof and most other services contained in the two supporting cores, vast areas of open floor space will be made available at upper levels for office use and at two basement levels for car parking. Each of the cores is to contain 500 cubic meters of concrete and 200 tons of steel reinforcement. The construction program provides for bridging between the two cores with sections of the floors, erecting the roof support structure which straddles and overhangs these cores, and assembling the floors one after the other at ground level. Then the floors are to be jacked up into position, with the top one actually going up first. The lifting is to be carried out by friction-type jacks like this one, pulling their way up 40mm diameter threaded high-tensile steel bars. On arrival into final position, each complete floor is to be suspended from hanging rods attached to 12 hanger points located around the perimeter of the roof. The load is to be transferred from these points by a series of raking bars to the central structure. Each floor is also to be given internal support from a number of steel billets located in sockets cast into the core walls. That was the plan, so how did it all begin? Back to our hole in the ground in Dame Street. As the job of site preparation goes on, all Dublin watches. Some more closely than the rest. a davy look-in on the way to school. First, the 50 by 60 metre site is surveyed, drained, and prepared for the core foundations. Rock has to be drilled and removed, and old brickwork taken away that had formed the cellars of the 19th century brick-built houses originally standing on the site. One of these structures, known as commercial buildings, had been built in 1798 and was for a time the first Dublin Chamber of Commerce and the Stock Exchange. It's decided to take apart and reconstruct this historic building, turning it sideways to front onto the public plaza, which will extend under the first floor of the bank. All of that, however, was back at the design stage in early 1972, when the main work was preparing the site for the foundations of the two great service cores. While all this was going on, other men were working deep in the ground in one of Sisk's own stone quarries, cutting and working granite for the cladding or facing of the building. This quarry is at Ballybrew in the Wicklow Mountains. The granite slabs are first cut and bush-hammered by mechanical means. Then stonemasons, whose craft is traditional to the area, complete the finishing process by hand. These slabs are stacked and ready for transport to the precast concrete yard of Breton Limited to be used as facing for the cladding units. Then they'll be on their way to Dame Street. At the same time, in Dublin's North Strand at Smith & Pearson Steelworks, structural steel for the bank has been fabricated. Here, high-quality CO2 welding has been used on one of the 12 hanger trusses for the roof. These highly stressed members are fan-shaped to spread the stress into the 300mm thick concrete plant room slab, which in turn transfers the load back into the cores. Back at the site, the core bases are still being worked on. These bases are founded on solid rock. The rock here was core drill tested to a depth of 10 feet. Each base incorporates 40 tons of high tensile steel reinforcement and is 750mm thick. The concrete arrives. It's skipped into position by the 160 feet high tower crane, the tallest one ever used in Dublin. Due to the confined area of the site, all the concrete is ready-mix supplied by the firm of Ready Mix Ireland. The concrete is vibrated and leveled. "120 cubic meters is used in each core foundation. All of the reinforcement used is cut and bent on site. In a month, the foundation for the first core is ready. Vertical reinforcement is fixed, and the firm of British Lift Slab is given the green light to go ahead. The big concrete mushroom is ready to shoot up. The first operation is to place door ope forms in position on the foundation of the first core. Then, a shutter module is built on site by Sisk's from drawings prepared by the British Lift Slab Company. The sections of this shutter are made by cutting standard sections to plan. The module incorporates a 1 meter deep section of shuttering for the walls. The module for each core was built on site in a period of a fortnight. Then, into the narrow streets hugging the site on 3 sides, come the first of the continuous convoy of ready-mix trucks, which will arrive at the rate of 1 each hour, 24 hours a day, literally pouring the 2 great concrete towers into the sky in a night and day operation that goes on for a fortnight. The first of the 43-meter high cores goes up in 9 days. The second takes only 5 days. These cores look simple externally, but inside they're very complicated. On each floor level there are 12 doorways, 14 duct openings, and 19 cast-in steel inserts to receive the billets to support the concrete office floors. Each core calls for 500 cubic meters of concrete and 200 tons of reinforcement. The British Lift Slab Company has provided for 3 platform levels in the slip forming module, the third one being a suspended inspection platform. The concrete is landed by crane on the top deck, an operation calling for very precise control by the crane driver and his mate on the ground. From this deck, where working materials are also stored, chutes direct the concrete to each compartment on the working deck below. Guides are set to direct the vertical steel reinforcing bars and door frames into the walls being cast underneath. On the middle, or working level, where the walls are being formed, are carpenters, steel fixers and the concreting crew, together with welders and the gang from British Lift Slab, a workforce of 24 people on average. After lift-off, a platform suspended below the working deck gives access to the wall surfaces and is used for checking the consistency of the concrete and cleaning out openings. Tarpaulins hanging from the top enclose the working level, protecting the fresh concrete below the lowest platform from damage by wind and frost. 48 friction-type jacks are used to lift the module. These jacks are connected to 3 central hydraulic pumps, which are controlled from the lift slab console on the working platform. The hydraulic fluid pumped up by them forces the jacks to climb, inch by inch, up 50-millimeter diameter fixed steel tubes, very much as the climbing irons of an electricity linesman move up a pole. Additional tubes are joined on by screwing them together as the shutter climbs. The stroke of each jack is 70 millimeters, and the control system ensures that no stroke can take place until all the jacks have completed the previous one. The lifting rate is between 150 and 450 millimeters an hour. Because the work is complicated and the job comes right in the depth of a very cold winter, British Lift Slab have set a target rise rate of the cores at 250 millimeters an hour. As the great concrete tower mushrooms up from ground level, people are amazed at the speed of its rise. At 350 millimeter intervals, the entire module is leveled. Jacks are adjusted manually to a datum mark on each climbing tube. These marks have been made previously using a level on the upper platform. An optical plumb is used to check verticality. It's clipped into stations at ground level to read target boxes fixed to the soffit of the platform. A plumbing accuracy of plus or minus 20 millimeters is achieved. As the shutter rises, levels are established by 4 steel tapes paying out from their anchor positions at the bottom and set to read the correct ordnance datum. Levels in the openings in each wall are clearly shown on heat-sealed drawings hung on the shutterings close by the work. The most critical items in these walls are the inserts forming sockets to receive the floor support spigots. About 95% are found to be within the required tolerance of plus or minus 50 millimeters. Work goes on 24 hours a day. When the cores are finished, the modules are taken apart. 8 castellated universal steel beams are dropped in at each level to span the 15-meter gap between the cores. These beams are supported on channels at each core. The channels bear on solid steel billets inserted into preformed steel sockets cast into the core walls. These 1.5 meter square precast concrete slabs complete the bridging operation. There are 60 of them at each level. The slabs will later be bonded together with steel reinforcement and concrete so as to act compositely with the supporting universal castellated beams. The bridging operation takes place during the first 3 months of 1973. Not the warmest place in the world on these icy winter days, the Aramac lift on one of its endlessly repeated milk runs to and from the sky. The roof design is a fairly simple one. 4 columns are erected at the corners of each core. These act as vertical compression members and are fabricated from 475 by 425 millimeter universal column sections. Macalloy bars are used as tension members to link the crossheads located at the outer end of each plant room hanger truss with crossheads located at the tops of each column. This arrangement results in the 300mm thick composite plant room floor with the vertical steel columns acting as compression members of a passive framework catering for symmetrical loading. Now to return to the assembly. The lifting operation is a tough and formidable one, for the base of each of the vertical structural steel columns is 37.5 meters above street level. As the load was too heavy for the tower crane, the lift is carried out with a 65-ton mobile one. Control is by radio link. Distances and heights are great, and the center city traffic noise never stops. Each of the columns is then fitted with its supportive bracing bolted down onto the core roof. Then comes the assembly of the horizontal McAloy bars, which tie the tops of the columns together to form the box-like structure bridging the two cores. The next major operation is the erection of the 850mm deep hanger trusses. These are shallow, prefabricated multi-web boxes fitted centrally over each truss. The truss is spanned out to a width of 3 meters to transmit the compressive force from the hanger points into the concrete plant room slab. Each of the Concord-like trusses is erected on a temporary diagonal hanger frame pending the insertion of the 16 40mm diameter raking McAloy bars which support each truss. As the hanger trusses are erected, welders are busy at ground level assembling the perimeter trusses. 2 of these are 45 meters long and were delivered in 3 sections for welding on site. The shorter ones, each 32 meters long, were delivered in 2 sections. The long perimeter trusses, 3 meters deep and weighing 17 tons each, are erected by 2 cranes working in tandem. Once again, very delicate control is needed in this operation. The perimeter truss is bolted to its seating on the hanger truss. After the perimeter trusses are in place, 68 infill trusses are erected. These trusses, spaced 1.5 meters apart, support precast concrete panels which act as permanent formwork for the 185mm in situ reinforced concrete plant room slab. The vast umbrella-like structure begins to take shape. This evening silhouette view shows how the sometimes rather harsh outlines of a great building under construction can be softened by the play of light and the mystery of shadow. The next step was to be the erection of the granite-faced precast concrete cladding panels to the plant room perimeter trusses. But at this stage, unfortunately, there begins a serious and lengthy interruption to the work. After many complaints that the building is exceeding its permitted height, construction is halted in October of 1974. To make the effects of the stoppage less serious, Sisk proposed to the clients that 3 floors should be assembled at ground level each time instead of 1, and this is agreed to. But all work is suspended in March 1975, pending the result of a planning appeal by the client. In April 1976, the workers return, and the big job goes on. At this stage, Sisks are asked to carry out major alterations at roof level. These involve removing the main roof envelope, leaving the interior structural system permanently exposed, a direction which calls for the complete redesigning of the plant room installation. And all this means additional delay in the completion of the building. The next major activity is the assembly of the floors. These are assembled at ground level on 12 support trestles and internal lifting beams in order to simulate final support conditions while each floor is still on the ground. Jacking rods are attached to the 12 hanger points on each floor and to the internal corner points of the lifting beams. Each of the 7 office floors is constructed from precast concrete panels resting on 850mm deep steel trusses. There are 64 such trusses and 12 hanger trusses on each floor. The perimeter of each floor is cladded with granite-faced precast concrete fascia and soffit panels prior to lifting. The soffit cladding units are placed on the ground before assembly for hoisting into place with winches. The fascia panels are erected by special purpose-built cranes which are able to operate under the overhanging structure. Trusses rather than beams are chosen on account of the high degree of permeability needed within the ceiling void for air conditioning, ducting and other services. The perimeter trusses, supported on hanger trusses, are cantilevered to the corners of the building. Before jacking up each floor, materials needed for finishing the building, windows, glass ducting and floor panels, are loaded for lifting with the floor, making the total lifting load each time 400 tons. The 50-ton BLS lifting jacks used to lift each floor are connected to 2 central hydraulic pumps and are monitored from a control console. If a jack fails to complete a stroke, its failure is indicated on the control console and the system stops at once. Each jack has a 200mm diameter hydraulic cylinder with top and bottom crossheads to carry the threaded lifting rods. Nuts in the crossheads are automatically rotated to take up the load. Each stroke is 50mm and the lifting rate can be up to 3 meters per hour. The 8-meter long lifting rods may be extended with couplers. A continuous lift is limited by these couplers which cannot pass through the jacks, so the lift is done in 7.5-meter stages. At intervals, the great load is temporarily parked. Jacks are released and the lifting rods are lowered. In this way, the 7th floor is parked on the 1st, 3rd and 5th levels before final positioning, and so on. Fixed lifting rods are suspended at the core corners to make possible the temporary parking by duplicating the rods in the jacks. At these temporary parking levels, split nuts are used to carry the load during the operation of rod dropping. Each floor is designed to encircle the bases of the twin cores, and when the jacks begin their lift, the floor slides up the cores like a napkin ring being pushed up a rolled napkin. After the 3 floors assembled during the planning dispute had been parked, the rest of the floors are assembled and lifted at 2 monthly intervals. The lift-off of each floor is a nerve-wracking business. All eyes watch as the great mast trembles slightly and then moves from inertness into a slow, slow climb. And the movement, as it continues upward, is accompanied by loud creaking sounds. Before each floor is transferred to its permanent supports, it's checked by sighting with an autoplumb from the ground and horizontal adjustments are made. The levels at which the perimeter of the floor is set take into account the extension of the McAloy bars on transfer of the load. The core spigots are inserted from a suspended platform under the floor. Once inserted and checked, they're welded into position. Installation of the perimeter glazing begins before all floors are in place. And now, as the pace speeds up, comes the finishing off of the McAloy bars. They're first wrapped in wax-impregnated tape, the hanger points are then clad with fiberglass boxes which are filled with a fireproofing material. The bars are then clad with preformed sections of fire protective material. The design for this was worked out by the structural consultants Ove Arup and Partners, based on information supplied by the British Fire Research Station at Harwell, where very extensive tests were carried out. The treatment is designed to give, under fire conditions, 1 hour's protection to the McAloy steel support bars. Finally, the whole assembly is covered with anodized aluminium sections. floor trusses are clad in expanded metal lathing and then sprayed with a fireproofing compound. At places where the ducting passes through the internal trusses, the openings needed are trimmed. And the lathing is finally sprayed with fireproofing material. Cavity floors are used throughout to give access to the trunkings in which run the power, phone and other service cables. Up on the roof is the main plant room, now redesigned, open to the skies, and completely cladded in copper. This is the building's powerhouse, the engine room that keeps it alive and breathing, getting rid of its waste products, warming its workers, and communicating internally and with the outside world. Air conditioning is designed on a grid system with input through anodized aluminium T units acting as diffusers for the incoming air. The grid is infilled with fiberglass, coffer-type sealing units through which the stale air is extracted. Light fittings are mounted centrally in these units. Meanwhile, external work is proceeding on the plaza, under which there's a cavity housing the air extraction ducting network from the basement car parks and also the plaza drainage system. Work also proceeds on the laying of granite sets on the plaza. These were cut to form fan-shaped patterns whose curves contrast soothingly with the austere lines of the great building looming overhead. This produces a softening of the outline which is carried further by the fountain, flower boxes and benches that also beautify the concourse. An imposing flight of granite steps leads up from here to the bronze-cladded main entrance to the foyer. Now, more and more of the Sisk operatives have moved out. The carpenters, concreting crews, steel fixers and welders, giving place to the incoming office workers. At last, the big bank is coming to life. The staff takes over. They go to work in the brightly lighted, air-conditioned offices, whose windows give a breathtaking panoramic view of sections of Dublin city, its mountains and its bay. They take their meals in the fine purpose-built restaurant and rest area in the annex building, which will keep alive forever the outward aspect of the commercial buildings that Joyce's Leopold Bloom knew so well. The interior of the restaurant building contrasts with the office areas to give a welcome change of environment to the staff during their rest periods. The walls in these areas are self-finished in boardmark concrete and the polished hardwood floors from Sisk's own joinery works. Working conditions in the big bank are, in terms of ordinary office accommodation, comparatively luxurious. On the third floor is the foreign exchange room, where clocks keep you up to date on world time and electronic machines on the global movements in the money market. This is the control centre for the Irish punt. It's almost too warm in the boardroom, where the view is the best there is and the carpet is a specially woven Donegal one. You can now drive a car down the ramp to the huge basement twin-level car park that's taking 1,000 cars off the city centre streets. The columns here, by the way, are hollow and contain air conditioning ductwork. Over the car park entrance ramp is the bank's security room, which monitors all services in the building. We've come a long way from our hole in the ground in Dame Street, and we've used a lot of steel and timber, concrete and cable, bolts and nuts, and sweat. But now, the big bank is finished.
I built a tower in Dublin right up to the sun. Steel, concrete, and time. I built that tower in Dublin. Now it's done. Buddy, can you spare a dime?